So, as introduced at the start of the presentation, the aim of this event, this webinar, is to basically run through what we perceive to be, or we see to be, the current normal, as we call it, within the marketplace for high pressure coolant installations on sliding head machines, and the issues, concerns, problems, shall we call it, that creates, and what we need to try and do to make processes easier to eliminate those issues. From there, we will then run through the AWL AFC systems to see how they actually help to overcome those problems. So first up, we go to the current normal, as we call it, and again, as we say, welcome to ARNO. Innovative sliding head tooling, as we've already mentioned, with the aim of improving efficiency, productivity, and reducing costs within that process. So the agenda for this particular part of the presentation, as we've said, is what we term the current normal. The solutions that we can hopefully provide to that current normal with AWL AFC tooling, the benefits that brings to you as the end user within your machine shops, and the general conclusion on that basis. So firstly, the current normal high pressure coolant setup. Generally, it involves a lot of complex, high-cost hose assemblies, which in turn tend to be slightly inflexible. We have long setup times, and they lead to excessive downtime because of the way that we have to install those solutions, the tip changes, the access to tooling, etc. So when we talk about complex setups, this particularly highlights it here. We have an external manifold, and as we can see, inlet feeds coming in, and multiple outlet positions which then feed to the tools. So very complicated in setup. Again, a range here of not directly fed through coolant but high pressure flood, but numerous pipe assemblies, hard pipe assemblies with quite complex bends within them, which again create issues. And here the same principle, a mix and match here of hard pipe solutions and high pressure hoses with quite bulky connectors. When we talk about inflexible, the problem with some of these solutions is that if you use a tool from a particular manufacturer, the coolant port will be in a certain position. If you use then a tool in the same tooling position but from another manufacturer, you will get a cooling port which is in a different position or even a different thread, which means a completely different piping solution. And all of this adds, as we say, to excessive downtime. So, as we've said, high levels of machine downtime, highlighted again here with the piping issues and some of the complexities that we get. So as we can see, similar principle to already shown, multiple hoses here which infringe on the workspace, which make access difficult, which make swarf conditions difficult. And again here, even with a highly specialized solution, we still have very complex connectors, long overhangs, pipe solutions getting in the way of the workspace. And when again we talk about swarfing issues, we see the pipe solutions here, but this is the issue it can create. Problems with swarf trapping within the workplace area, gathering on the pipes themselves, getting in the way of the workpiece component. And this leads to issues whereby we get workpiece damage potentially, we actually get damage to the hoses themselves, and issues where we have to keep stopping the machine to clear the swarf, which again leads to increased downtime, reduced uptime, and a lack of productivity and process stability. From there, we also potentially encounter handling and clamping errors and stability problems when we utilize the cooling systems. Two other options that we have, obviously, is the standard clamp on that comes with the machine. Now, this is the strongest method of clamping. As designed by the machine tool manufacturer, you would expect that to be the case. But you can get issues with these systems here because of these thin sections that we see where they warp, they twist, they crack. So they have to be replaced, and also if they're not replaced, we do again lose clamping pressure because of the distortion of this clamping area here. Other two-piece solutions that are in the marketplace utilize these clamping wedges, which actually replace the OEM solution. The issue here is that we only have a small contact and clamping area and an offset screw position with a reduced cross section. And the problem with that potentially is that the clamping pressure applied is nowhere near as strong as this solution, which actually causes issues with tool push out, not maximising the potential of the machine for its speeds, feeds, application area, because we lose that gripping pressure and the handling capacity. So the current normal setup, to confirm what we've just spoken about: high cost complex setup requirements, restrictions on the tools that can be used. As we've said, different manufacturers' tooling solutions have different port positions, have different threads. So when we move from one to the other, we have to restructure the piping assemblies and the hosing. This gives us some difficult, time-consuming changeovers, and the downtime gets increased. We also have non-repeatable processes because we have to remove the tools from the machine, reinstall the tools, reset positions. And again, this all leads to excessive downtime and increased production costs, which impinge on the business itself. So what are we looking at here is in terms of the tool changes themselves, the cost of that particular tool change. So what we're looking at is a generic setup. Obviously, different people will have different setups in their manufacturing requirements. They may be different to this in many respects, but this is a guideline based on practical experience. So if we work on one insert change per day, and we have 6 tools in use on each rail setup, and we have 5 minutes per tool change. Now the 5 minutes we will see a little later in the presentation is based on actual practical experience with a video that we show that relates to the particular tool change for a setup that we have. So we're talking 6 tools, 5 minutes per setup per day. That gives us 5-day production. So 6 tools, 5 minutes is 30 minutes per setup, 5 days production, 150 minutes per week per machine. So 2.5 hours lost in productivity per machine per week on tip changes. If we stretch that out a little farther to a 45-week production year, obviously some will do more, some will do less. But if we work that out at 150 minutes per machine per week, 6,750 minutes, which is 112 hours. If we work that on a nominal £60 per hour, we're effectively adding cost to the process in the region of £6,750 per annum, purely on time lost per tool change. Now obviously, if you're changing inserts once per shift, you're machining more difficult materials, that again increases the cost. If you're running 3-shift systems, again that increases the cost. But if we just work on 1 tool change per shift still, but 3 shifts, again this begins to treble, and all of a sudden this £6,750 increases quite quickly to £13,000, £20,000 per machine. And on multiple machine setups, we can see that we get a very high level of cost associated with machine downtime attributed to tip changes. So how can we improve that setup? Well, obviously, if we're looking at the rail, if we can supply through coolant directly to the rail without the need for hose assemblies, pipe connectors, that will improve our processes and our downtime. Also, if we can supply coolant to every single tool, we improve the machining process for every tool. Because generally within a high pressure setup, there's only normally 2, maybe 3 tools that are set up because of the difficulties of the piping configurations and access to the tools that those piping configurations actually lead to. From a cutting tool standpoint, if we can get fast, effective, simple tool changes with a high level of accuracy and repeatability and targeted through coolant to the cut point, we improve the machining process, we reduce the downtime, we improve the tool life and the swarf control, all of which hopefully goes to improving the processes that we've seen and the issues that we've seen in relation to a standard high pressure coolant setup. That gives us an end goal basically of reducing downtime, increasing uptime, which in turn increases productivity and reduces production costs. So back to the start. Now, what do we have within the ARNO portfolio with our AWL AFC tooling systems that can go towards improving these processes, reducing and eliminating the issues that we've highlighted within this current normal? Now what we have is a two-pronged approach, shall we say. So we have the AWL rail, which we see here, which is OEM compatible dimensionally, so it fits onto the existing machine. The lengths, diameters, depths, widths, offsets are identical, so it's a repeating process. We don't have to reset anything in that respect. And we combine that with a two-piece quick change tooling system that allows through coolant supply to each particular tool as required. So the first element that we will look at is the coolant supply to the AWL rail that we've spoken about. Now this particular video actually shows how the coolant is fed into the rail, how that in turn feeds into the tooling systems, and the flexibility and ease of use that we have within the process. So you will see here the coolant fed into multiple port positions. Each particular rail has a variety of areas where the coolant can be fed in, so it can be optimized to your process and your machine. Ports can be sealed, ports can be opened to give us the access we need. The rail itself can be split in two with this screw, which effectively cuts the rail in half. So if we can have twin coolant feed, it allows us maximized pressure to each particular zone of the rail. So again, we get in that optimum pressure. Each location can be opened or sealed to suit. So we can have it to a specific tool location, we can have it open to all tool locations, but there is flexibility within the system to allow us to access what we need and how we need and when we need. So that covers the rail itself and how the coolant is fed, the flexibility that it gives us in our individual setups. We've also spoken previously about clamping issues, whereby we have the strongest clamping solutions, but the weaknesses that potentially that can bring, and also other twin clamping systems and the effect that that has. You will see here now we're looking at the wedge clamping system, and as you can see from this rail, we have two specific high tensile stainless wedge clamps, both the cutting piece and the wedge unit at the back, which supplies the through coolant, and this shows how that system works. So again, as we say, high tensile screws, stainless steel, two for the stop at the rear, two for the cutting tool. These are quick release, so basically 180 degree turn, the clamping pressure is released, the tool slides from position, we locate it back into the slot, and again clamp up with standard Allen key. And as you can see, an angle contact face locks us down against the full contact of the shank position. So we're having maximum clamping pressure against the rail, which minimizes potential deflection and gives us stability in the cutting process. Also, we've spoken about accurate indexing repeatability. The two-piece system that we have here has a few features which allows us to give guarantees as to that flexibility of repeatability. As you can see again, quick change tooling, quick release. The tools themselves have an angular contact face which guarantees repeat location. The coolant nozzle in itself also is flexible. So what that means is instead of being a rigid location, the tools can be located quite easily because we have a large contact area on a taper face which gives ease of location. All tools themselves as well are the same dimension. So whichever tool you use in every position, they're all 70 millimeters in length, they all repeat to size. And what you find as well with that, in that position there, the repeatability is guaranteed to within plus or minus 0.5. Quite often it's more accurate than that as well. But what that does mean is that if you are doing a roughing cycle or a general open tolerance cycle, the need to reset your datum and your offset once you've indexed the tool is removed. Obviously for finishing applications it's still recommended, but what we do find is very quick change over times, but because of the accuracy of index, we no longer need to reset our datums and offset positions. Now, obviously we've now gone through the rail itself, how the coolant is fed to the rail, the flexibility, the strength and rigidity of the clamping system, and the flexibility and ease in use and accuracy of the system. The coolant is supplied to each individual tool location, and what you have here is the coolant fed into the rail. All of the piping is hidden behind the rails and the guards, so there's nothing in the way of the workspace. The coolant is fed into the backstop with an adjustable location here, so you can offset different lengths to suit your application. As long as the guide rail is between these 2 points, we get through coolant to each tool. And as we can see, the coolant supply is direct to the cut point for every single tool. So maximising swarf control, coolant to the cut point, which gives us increased tool life, allows for longer tool life, allows for increased speeds and feeds, and enhances the process across the board to give us a better tooling solution. One of the primary elements, or the weak points, shall we call it, within sliding head applications is actually the part-off. Because the weakest tool in the process, shall we say, it tends to get used as an offset position as well. And also, when a part-off tool is buried within a component, 32mm for example, stainless steel, titanium, Inconel, coolant supply to the cut point is absolutely critical. And with most systems, that coolant supply does not directly get to the cut point. With ARNO, we have a patented system known as ACS, which gives us direct coolant supply to the cut point, guaranteeing optimum process. And this video highlights and shows how that coolant is fed and the difference to some of the other systems within the marketplace and the potential benefits that it gives. So again, as we can see, coolant fed through the tool directly to the cutting head through clamp tooling system. And as you can see here, it is fed through the base of the clamp directly across the top of the insert, giving coolant supply to the cut point. These are alternate options here. So this is the flood coolant, which basically hits the top of the insert, and another coolant system through clamp, but not through this area here, so it does not directly get to the cut point. As we can see here, the coolant jet is straight across the top of the insert, guaranteeing optimum coolant supply to the cut point. And you can see here again now on this particular area how that works. What we maintain is a reservoir of coolant, if you will, directly between the machine, the insert top face and the interface between the material. So we're guaranteeing optimum coolant supply and optimum swarf control and chip evacuation. As we can see here, you actually have a visible gap where the coolant isn't contacting the area that it needs to be at, which is the interface. So it keeps the cut temperature down, which improves tool life, but also evacuates the swarf. And the patented ACS system gives us that process stability and coolant supply. Now, we speak about tool changes, and this is where you will see the 5 minutes that we came up with previously. The first part of this video actually shows the simplicity of the tool change. Undo the clamping screws, the tool itself removed from location, slides back in, repeats within this 05mm as we say, but very simple, ease of access, ease of use. And this is the view that you basically see with the rail on the machine. No pipes, no hoses, again shown here on this particular video. This now is a rail that is completely plumbed in, but as you can see there is no obstructions in the way, whereas here on this particular tool we have a standard pipe assembly. Now what this video shows is the speed, shall we say, and the ease of tool change timed to give us a cost potential or an indication of downtime for a tip change. So as you can see here, quick release screws, open up, slide and release the tool. Obviously here we're having to undo the pipe assembly, remove the pipe assembly, clear the clamping connector, the bolt-on screws, etc. This non-productive time is basically a tip change. So the tool is out of the machine, 1.5 minutes to change the tip, locate it back in the machine. So this is the time that we're looking at to actually remove and replace the tool. So as you can see here, it's taken us roughly 30 seconds to actually get the tool out of the machine. Here we're talking 30 seconds and the tool is out and replaced. So including a tip change off the machine, we're looking at 2 minutes total tip change time. On this particular setup here, as we can see now, we're having to relocate. So we've had to reset the position of the tool against a component for the offset position, reconnect the pipe, all of which is taking time. We then go away, set our datum, and from there, we're talking roughly 3.5 minutes to actually change a tool, plus the tip change time gives us 5 minutes. So this is the 5 minute data that we had when we looked at our initial cost analysis. But as you can see, 3 minutes saved per tool change. Here we have a 5 tool setup, so that's 15 minutes per changeover. If we're talking 3 changeovers per day, that's 45 minutes per day, 5 production days per week. The costs begin to improve, the setup times reduce drastically, so the process stability also increases. We can further enhance these savings if we run sister tools. So instead of taking the tool out, changing the insert off the machine, then replacing, if we have a sister tool in situ, we take out the tool, we put in the tool that is reset, and we go again. So this 2 minutes here basically becomes probably no more than 45 seconds. So an even greater enhancement on savings in changeover time, productivity increases. So the AWL AFC system benefits. If we look at the tooling rails, we have direct through coolant supply to every tool within a controlled location, so sealed location specific to that particular port. Direct through the manifold to the cutting tool, so there is no pipe work associated. Individual high strength clamping wedges for stability of process, quick release clamping screws as well for ease of access. It allows us to utilise the AFC system with some very fast, simple tool changes with the AFC tooling. And again, no complex and time consuming initial setups. Once the rail is in situ and has been installed, that is it then, the coolant is in place. So your changeover time, your setup time is simply how long it takes to replace a tool. The second part of the solution, the AFC quick change tooling, again, simple, easy tool changes. There are no restrictions as well on the type of tool that can be used. The tool slots within the rail conform to OEM specifications in that they are an open slot, 12mm square, 16mm square, 20mm square. So you can utilise other tools within the rail. You are not restricted to having to use ARNO tooling. So if you have a threading solution from another supplier, as an example, that you prefer, you can utilise that tooling solution within the rail. You do not have to use other elements of tooling to suit that require different port positions. You know, you can use your standard burnishing tools, knurling tools, etc. They all fit within the rail, so that gives us ease of use again. Stable and accurate processes because it's a reliable changeover, simple and easy to use. And again, back to this point of significantly reduced downtime allied to significantly increased uptime, which improves our processes, which improves our cost to benefits and cost ratios, giving us more stable processes. So to sort of highlight and show what we've spoken about here in terms of ease of use, ease of access, we have a few before and after images of actual real life installations, so you can see the difference that the utilisation of these systems make. So again, here we have a Citizen machine. As we can see, external manifold, primarily flood coolant supply here, but again we have various pipe connectors and issues, hard pipes which need to be bent, but again we're only looking here at flood coolant, which doesn't give the real benefits that you can achieve with high pressure coolant by the direct coolant supply. This is an AWL rail installed, so we have a single coolant in feed, but as you can see, every tool now is coolant fed. No hoses, no external manifolds, total open ease of access, no swarf traps, and again, a much more open working space and environment. So again, you can get the spindles closer together as well for short parts, for example, which gives us better utilisation of material in the machine. We don't need such an overhang to be able to get to produce those parts. We're looking now again at Star SR10, and as you can see, this is a multiple hose system, shall we say. We have a flexi hose with a hard pipe connected here, and then 2 flexible hoses, but again bound together, which means if you want to change systems, you have to reduce or remove this cable tie and then start again from that position. But also, as you can see, quite obtrusive coolant connectors here, which actually get in the way of the clamping screws. So ease of access for tool change is impinged by looking at this system. What we have here, similar principle again, single coolant in feed based on setup, but every tool is now coolant fed, and we remove this access problem here. So the hoses aren't in the way, we don't restrict access to the clamping screws, and everything is open, ease of access, ease of use. Same again, another style machine here, but again here we have one coolant in feed only, and again then external pipes. Obviously we have the issue for the pipe bend, we only have flood tooling supply, but again these pipes are actually directly in the way of the clamping screws, making tool changes and access to those tools less than favourable. Similar position here, feed into the rail, and as we can see, we've looked here at different feed positions, from one to the front face here, one to the front face here, one to the side. So this is the multiple port inlet that we say that gives us that ease of use and flexibility of use. But again, repeating a theme, completely open access, all tools free to access, total ease of use in terms of clamp location, much simpler, much easier to use. A little more complex setup here, again an external manifold. We have two inlets coming into the manifold area here, so again we have these hose supplies and issues, and 4 feeds out. But again, that then entails 4 hose assemblies, difficult setup potential, issues in terms of tool change, how many we have to replace. But as we can see here, directly fed into the tools, but this again shows the clamps problem with the clamps not accessible due to the hose connectors blocking that access. Repeating a theme here, as we've already said, coolant is fed here behind the machine guards, so completely obscured from view. Total open ease of access again. Every single tool free to access, all clamps easily accessible, and coolant supplied directly to the cut point with every tool. This last one probably highlights the issue more than anything. As we can see here, we have a main feed into this manifold, but when we look at this here, this is a very, very complex solution. Ease of access greatly reduced and changeover times massively affected. When we look at the solution that the AWL provides, we still have the manifold in feed, as it were, or the main access feed comes into the rail here, but now all tools have coolant feed, but we no longer have this multiple porting position here. So again, just a few examples really showing the before and the after, and the issues that we've spoken about that we can get with high pressure setups in terms of difficulty of setup, difficulty of access, non-coolant supply to tools, etc., etc. So, in conclusion, AWL, AFC systems combined can give you the process improvements and associated cost reductions that we're all trying to achieve. We all need to improve our processes, we all need to reduce costs, and probably the best way to do that is by improving the processes and improving the way that we do things. Utilising the AWL, AFC systems, we get those quick and simple tool changes. We reduce the machine downtime, increase the uptime. Much more stable process, giving us productivity improvements, allied to the flexibility of use, and then we get the increased tool life, reduced cycle times due to that coolant supply that we get direct to each cut point. So, enable you to enhance your competitive edge. ARNO Tooling Solutions, AWL and AFC, hopefully, as we've shown, highlighting the benefits of those systems, the features of those systems, and what it can bring to your production environment in terms of the ability to improve those processes and reduce costs. All that remains to say is thank you for your interest, and we will now move on to the question and answer session as we spoke about previously.